Hey everybody, this is Mr. Piercy, and what we're going to be taking a look at in this video is how you can use trigonometry with something called the law of sines to evaluate and find sides or angles of triangles that are not going to be right triangles. So now what we've done up to this point in our material with trigonometry is we've established that there are three basic ratios, sine, cosine, and tangent, with right triangles that we can use to find missing sides or angles of a right triangle. Well, now we're moving on to something called the law of sines, which will allow us to essentially perform the same thing that we were doing with normal trigonometry with right triangles, but it will allow us to find missing sides and angles of triangles that are either obtuse or acute. Now, if we happen to have a regular right triangle, I wouldn't bother using the law of sines. I would just use my normal trig ratios. But let's take a look and see what the law of sines are. Now, there is a simple investigation that we could do to justify where the law of sines comes from. But that's not part of this material, so I'm not going to try and recreate it here. But essentially, given that we have some triangle ABC, I can say the sine of angle A over the side A, that ratio will be equal to the ratio of the sine of angle B over side B, which will be equal to the ratio of the sine of angle C over side C. So that's kind of what we're looking at in a triangle like this, is we can essentially have a proportion based off of these angle and side measurements that are given to us in order to find a missing side or angle of a non-right triangle. Now, the law of sines is very useful. However, it does not work for every possible triangle. So let me show you the combinations of parts that we can use for finding sides of, or when we can use the law of sines. So let's say we have a triangle where we're using the combination of an angle, an included side, and an angle. Okay, so this is just a generic kind of triangle here, where we're looking at a side, some angle, another angle, and the side included between them. Okay, so if I have this combination of angle, side, angle, that is when I am able to use one of the instances in which I am able to use the law of sines. Another combination of parts that we can have for the law of sines is going to be angle, angle, side. And hopefully these abbreviations are going to ring a bell from things that we did with triangle congruence in previous lessons. But here I'm going to have two angles and a non-included side. So here I might have this angle here and another angle here and a side that is not included between the two of them. That's what we're looking at when we say angle, angle, side. And the last one that we're going to look at here is the combination of side, side, angle. Now, speaking of triangle congruency with the parts that we had, side-side angle was one that we said could never be used to show congruency in triangles. And there's a reason why. There is something here referred to as the ambiguous case, where you could actually have two sides and an angle that's not included between those two sides, and you could actually, in some instances, depending on the size of the angles or the sides of the lengths of the sides, I should say, it is possible that you could create two separate triangles. Now, our curriculum is not going to go deep enough, or I should say it's not going to go as deep as what you might see in, say, a real trigonometry course where we're talking about this here. So with this combination here of side-side angle, there's something called the ambiguous case. We really won't see much of that. However, I will include a link or a separate video in your assignment post that explains what the ambiguous case is. And I'll talk a little bit about it when we see the side-side angle combination. But let's go ahead and jump into an example here. Okay, so we have our ratio sine, and if you wanted to, the ratio that we have here, we could reverse them. We could turn them upside down and say side A over sine of angle A is equal to side B over sine of angle B. But this seems to be the commonly accepted way of expressing it. Like if you were to Google what the law of sines was, typically this is how you see it, as the angle over the side. No particular reason why, it just is. So taking a look here, what we want to see is, in this case, we're looking at here an angle-side relationship here, where they're giving me this angle here at 35, this angle here at 71, and this side here at 12. So two angles and a not included side. And what we're asked to do is just find the length of this side that's opposite of the 71 degree angle. Now, if you want to, you could label these, however, in whatever order that you wanted to. You could say that this is triangle ABC like this. So that way it makes it a little easier to see how you're going to label things. But it's not particularly necessary to label them, something like this. We could just jump in with sine of 71 over x or whatever. But since I've labeled it, I'll go ahead and say the sine of angle A over side A is equal to, and in this case, they gave me, the way that I have it labeled is angle C, so I'll say the sine of angle C over side C. And substitute what we have here. So angle A is 71. Side A is what I don't know. That's what I'm looking for. Sine of angle C in this case will be sine of 35 over the side opposite of it, which in this case would be 12. And then we'll cross multiply and divide. So here, when I cross multiply and divide, I'm going to wind up with, let's see, how is it going to be? We're going to wind up with 12 times the sine of 71 divided by sine of 35 to equal x. Now, I probably should, I would show my work here, and I'll do it on the next example here. I just kind of ran out of room by writing the rule first, but this is what I end up with when I do my cross products. Now remember, we are doing trigonometry in degrees. That's what the angle measures are given in, so we need to be in degree mode on your calculator, so just make sure that you're in degree mode on whatever calculator that you're using. And here I'm going to just type it in exactly as I have it written on my paper. I'm going to hit my ratio button on my calculator and say 12 times the sine of 71, and I'm going to divide it by the sine of 35, and I'm going to hit enter, and I'm going to get this value here of about 19.782. So that's what we're looking for here. We would say that x is approximately equal to 19.782. So let's take a look at the next one here, example 2, and we'll try and fit a little bit more space in here. Now this time I'm not going to bother labeling the sides of or the angles A, B, and C. If you want to, if it helps you out, by all means go ahead and do it. We're just going to see here that in this case they're giving me this side here, they're giving me this angle here, and they're giving me this angle here. So again, we're dealing with an angle side situation, which lets me know, hey, that means I can use the law of sines here. So in this case, I can say the sine of the 18-degree angle over its side of 5 is equal to the sine of the 114-degree angle over its side opposite of it to be x. And now we cross multiply. So this is where I'll do a better job of showing my work. We're going to say x times the sine of 18. So x times the sine of 18 will be equal to 5 times the sine of 114. And to get x by itself, at this point, we will divide both sides by the sine of 18. Which will result in x to be equal to 5 times the sine of 114 divided by the sine of 18. And this is where we go to our calculator and see what it tells us to get. Okay, again, I'm going to hit my little ratio button that my calculator has, and I'm going to type it in as 5 sine of 114 in the numerator over sine of 18 in the denominator, and I'm going to wind up with about 14.781 units long. So here x is approximately equal to 14.781 units long. So you're starting to get the hang of it here? I'll do one more here. I'm going to go ahead and do the third one, and then I'll ask you guys to try and do examples 4, 5, and 6 just to see, how you're coming along with it. I mean, you have to have some kind of an independent practice with this. So let's take a look at what we have here. What combination of parts are they giving us? Here they're giving us an angle, here they're giving us an angle, and here they're giving us a side. So this is a third example where we're using the angle side combination of parts to justify using the law of sines. So setting up my proportion, I'm going to say the sine of the 73-degree angle will be over its opposite side of 20, and it will be equal to the sine of 59 over its opposite side, which is x. So cross multiply, and I'm going to get x times the sine of 73 to be equal to 20 times the sine of 59. Divide both sides by the sine of 73, and I'm going to get x to be equal to 20 times the sine of 59 divided by the sine of 73. And I'm going to go to my calculator again because, here I would stop if I wanted an exact answer. But on my calculator here, we're going to say 20 sine 59 over sine of 73. And 17.927 is what we're getting here for the length of side x. 17.927. Okay. So go ahead and try giving the next 3 problems a go. See what you're able to get on problems 4, 5, and 6. Pause the video as you work them out, and when you're ready, hit play and check your work with mine. Okay, so presuming that you've done what I've asked you to do, here are the next 3 examples worked out. Now here they did make us go the extra step to identify the angle that's actually going to be opposite of the side that we're looking for. So for instance, here on example number 4, they gave us these 2 angles, but the side that we're looking for, the angle inside of the triangle wasn't given to us. But we can find that with the triangle sum theorem, where we say that the sum of the three angles have to be 180. So we take these two numbers and subtract them from 180, and we get a 31-degree angle here. And that's how we're able to set up our proportion of sine of 96 over 27 is equal to sine of 31 over x. And then solving for x in this case gives us just under 14. Here we get just under 23, and here we get about 29.5. So hopefully things are starting to kind of pick up for you here. If you have any questions, of course, make sure you write them down so that way you can, you don't forget them and can get in touch with me and let me know what you're looking for or what you need help with. But let's take a look at the next couple of examples here real quick. I'll do the next 4 for you, and then there's 4 more that I want you guys to try and do on your own. Now, here again, they're kind of giving us the side here, this combination, but they're not giving us this angle here, so I do need to figure out what that angle is. So if I say 180 minus 117 minus 23, this will give us an angle here of 40 degrees. So that'll give me sine of 40 divided by the 29 to be equal to the sine of 23 over x. So here when I solve for x, I'm going to save a little bit of time by not writing out all the discrete steps that we're going to do. Multiply by here by x, multiply here by 29, and then divide by the sine of 40. And I'm going to wind up with x to be equal to 29 times the sine of 23, all of it divided by sine of 40. And going to my calculator here for the answer, we're going to get an approximate value. So let's see, 29 sine 23 over sine of 40. For number 7, I am getting about 17.628. Moving on to the next one, number 8. Here again, the side that they're giving me for, here we have angle, side, angle. And we had it, I don't think we had angle, side, angle in the last one. Here we had, we had angle here, a side here, and an angle here. So we are using the angle, side, angle combination here. Okay? But we need to figure out what this angle is here because that's the opposite of the side that they gave us. So again, the triangle sum theorem, take the two given angles and subtract them from 180. And in this case, I'm going to get that third angle to be 80 degrees. So here I'm going to say sine of 80 divided by the side opposite of it, 18, will be equal to the sine of the 39 divided by x. So again, I'm going to save myself a little bit of steps here by doing all of the work kind of simultaneously. Multiply here by x. Basically, these two things are going to trade, and this is going to come up here. So I'm going to wind up with x is equal to 18 times the sine of 39, all of it divided by 18. Nope. By the sine of 80. Let's see if we can fix this here. Sine of 80. There we go. So here when I go to the calculator, 18 times the sine of 39 over the sine of 80. In this case gives me about 11.5, I'm going to get 11.503. Okay. Now, here what we're moving on to is we're looking for angle measurements. And what you saw with right triangle trigonometry, and whenever we were finding an angle measurement, is you had to use the inverse sine, cosine, or tangent to actually find the measurement of the angle. And this will be no different, except in this case, because we're using law of sines, everything is going to be inverse sine in order to be able to find our angle measurement. Now, if you notice here, they're giving us a side here, they're giving us a side here, and they're giving us an angle that we have here. So this is that side-side angle combination that we could not use to prove triangles congruent to each other earlier in our geometry curriculum. But we can use this combination to find the missing, in this case, angle. So what are we going to look at here? Let's go ahead and find that. We're going to say sine of x over its opposite side of 9 will be equal to the sine of 77 over the side opposite of it, which is 14. Now we cannot do the Pythagorean theorem to find out this missing side here because there's no way to know that this is a right triangle. So when we multiply, essentially I'm going to just take this 9 and multiply it here. I'm going to leave that 14 because if I multiply it, I'm going to just wind up dividing back by it. So here this will give me the sine of x to be equal to 9 times the sine of 77 over 14. So I need to get x by itself. So here I'm going to say x will be equal to the inverse sine of that whole expression, 9 times the sine of 77 divided by 14. And going to the calculator here to show you how I'm going to type it in. Okay. I'm going to say hit my ratio, but don't want to hit my ratio button yet. I want to say inverse sine. Then inside of the parentheses, I'm going to hit my ratio button, and at the top I'm going to say 9 times the sine of 77. And in the bottom, I'm going to put the 14. And I don't need to bother closing the parentheses because the calculator will assume I'm doing that if I just hit enter here. So if I do, I get an angle measurement of 37.8 degrees. So here I'm kind of running out of room at the bottom. So here up at the top I'll say x is approximately equal to 38.8 degrees. So let's move on and try the next one here and see what we end up with. Now in this case, I'm going to say that this triangle is not the only triangle that we could have created where this angle worked out to be 38 degrees, or I'm sorry, where this side was 14 and this side was 9 and this side was 77. We could have created another angle here, and that's because this side here is, no, maybe I'm saying that backwards. Let me double check on that one here, because we can look at the sides depending on what side is what to see what those are going to be. Give me just 1 second to make sure I'm getting my... Okay, I just wanted to take a second to make sure I was going to give you the correct explanation here. The side-side angle combination is when we have the possibility of having more than one triangle here. So if I look at the side of the included angle, or the angle that was given to me, I basically want to say, okay, for the side that they gave me, is it smaller or bigger than the side that is opposite of the angle that I don't know? So in this case, because the side that they gave me with the angle that they gave me In this case, because the 14 is greater than the 9, that means there's only one possible solution here. If it had been the other way around, if this 9 and the 14 had been swapped, where the side opposite of the angle that they gave me was smaller than the side opposite of the angle that I was looking for, then that's a clue to let me know that I would have two solutions as opposed to one solution for that particular triangle. But let's go ahead and take a look at this next example here, and then you can try working out the next four on your own just to see how well you're picking up with it. We are looking for this angle here, so looking at the side here, again, because this side that's opposite of the included angle that they gave me, this 31 is larger than this side here that's opposite of the angle that I'm looking for. This should be a clue that because the side opposite of the given angle is greater than the side opposite of the unknown angle, that here I'm going to say that there should only be one solution. So setting it up here, I'm going to say sine of x over the 15 will be equal to the sine of 126 divided by 31. And then we'll cross multiply. Now here, because x is right here on the left side already, I'm basically going to just take that 15 and multiply it to the other side. So that'll give me sine of x to be equal to 15 times the sine of 126 divided by 31. So to get x by itself, we say x will be equal to the inverse sine of 15 times the sine of 126 over the 31. And again, I'm going to just jump to my calculator here so we can see how we're going to type it in. I'm going to say inverse sine of the ratio of 15 times the sine of 126 divided by 31. And here I get 23.0 degrees. So here x is approximately equal to 23.0. Do I need to include the 0.0? Well, did you get exactly 23? If you did, then fine, but I would include the 0 for my rounding, for my one decimal place for angles. So here are the last four examples of trying to find the measurement of an angle. Go ahead and try answering these, work them out on your own, and then when you're ready, hit play and check your work with mine. And here you go. Hopefully your answers and my answers are comparable. You should be rounding appropriately to the highest, number, rounding up or rounding down, depending on what number came to the right of the first decimal value here. So here I'm getting just under 50 degrees, a little bit over 80. This one I got just over 59 degrees, and the last one about 22.7 degrees. And that is essentially going to wrap up all of the possible examples that we would have. The one thing I kind of want to point out, taking a look at example number 11, okay, wait, no, there was one that I thought where we would have here. Nope. Here we go. On number 12, and no, not on number 11, but on number 12, the side that is opposite of the given angle is smaller than the side opposite of the angle we're looking for. So because this number that this side is less than this side, this tells me that this one I'm going to have more than one possible triangle with these dimensions on it, where I have one side with 12, one side with 28, and one side with 25. Basically what would happen is this side right here, this 12, would kind of be swung this way here to where it would still be 12 units long, but and you can see I'm kind of bleeding over here. The angle that we would wind up with here would be an obtuse angle rather than an acute angle. So this angle would be much smaller than the 80 degrees that we found, but it is possible for this one to have two solutions. Okay, same thing with 14. Nope, not with 14. I'm looking at it backwards. Yeah, so this is, I think, the only one that really shows that we're going to have two possible solutions on number 12. So if you really want to understand the ambiguous case, make sure that you watch the related video that I'm going to post with this. And anyway, that'll wrap it up for this. Thanks for watching, guys. I hope you learned something. Take care, and we'll see you soon.